the support. And so this is, for example, this is XA, and here it's XB. So last time we have learned is this. This is the loading of the beam, something like this. So we clamp here, we apply the loading. And we know for this case, the distribution of the bending is not uniform because the distribution of the bending is not uniform, so that will induce shear stress. So for this case, this is the distribution of the bending and distributions of the shearing like this. So this is M. So now the situation like this. Okay, and again, we expect at any level, for example, this level here, we will expect that the horizontal force, the directional force exists. And this force will become zero when we have the pure bending. But this is not the pure bending. You can see the bending basically varying from place to another. So this is not pure bending, so we expect they should have a directional force. And this directional force actually is obtained by taking the bending stress on this area and the bending stress on this area. This magnitude for this example is bigger, this is smaller. So which means we have the direction, go that direction to balance the things. Based upon this delta H, we'll be able to calculate this one will be equal to VQ times I times I forgot. Huh?
Isn't it XB minus XA?
Okay, so let me say this is delta X. So that's it. Okay. So this force, and again, that is due to the balance of the bending stress on this side and the bending stress on this side. Okay. And in the derivation, I believe you can look at from the textbook right now or refer to our lesson of last time. And from here, we simply, last time we introduced is this is a total force. So the total force divided by the total area. For this case, for example, say, let me put into 3D. So for this case, this would be the 3D and beam. Okay, those, for example, the beam has the thickness T. So that means we know that the average shear stress will be delta H, the force divided by this area. And that area equal to how much? Delta X multiplied T. So that's one leading into VQ over IT. That is the equation we obtained, and today we're going to do the exercise for applying these equations. But one more thing I want to introduce to you as the definitions. Here, there's an intermediate information I'd like to provide to you, and that is a very straightforward definition. Simply, we define the Q is called the shear flow. Shear flow is defined by the force, this force divided by the length. Basically, this is the total force. This is called the shear force. This is called the shear force per unit length. So basically here is we just try to scale this number into the unit length. For example, if this dimension is 1, then the total force here is called the shear flow. Basically, shear flow is that force applied to the unit length. That's it. Okay? For example, if this has a 5 units, then the total force will be 5Q. So that's the meaning of Q. Okay? Okay. So that's the definition. So here we have the shear flow, and later we're going to use this information. So here the shear flow, let me further write it down, is V2 over I. So we have this equation. We have shear flow, this equation. So those one will be used for our calculation. So I keep the formula here, then we can look up the examples. Or okay, we'll look at this one. Where's mine? Never mind. Let me write it out on board. So we'll look at this one. This could be similar to one of your homework examples. So if we have a beam, and that is the I shape on the cross section. And on one side, that beam looking like this. And here is the simply supported. And here we have the loading. P equals 1.5, and kilonewton. And here is 0.4, 0.2, and 0.4 in meter. So basically, these are I-beam, and from the front view, basically this line and this line looking at is the H here and the H here. So that's a drawing of this. And for example, if we select a cross section NN here, NN is a position arbitrary, but as long as in the first segment. And for this case, we want to calculate on section NN, we want to calculate what is the strain stress along the AA and along BB. So here the question is to calculate, find the strain stress along AA and the strain stress along BB. So this one basically is similar to this case. We have the beam like this, and we pick a cross section. For example, the cross section is here. We pick this cross section here. And on this cross section, you can see, for example, this is the side of the section. The bottom side could be representing to simulate the edge AA here on this one. So if I would take another piece, the thicker one, okay, I couldn't get it out, the BB would be the level at another portion we pick. Okay, so basically AA and the BB represent is the different level, different depth through the beam. Okay, so that is the case with the meaning of those symbols here. So we want to calculate, and for using this example, I want to calculate this formula. Okay, for this formula, by tau, this is the generic VQ over IT. And here the V is the transverse loading. On the sections in NN. Okay, so which means right now we pick the AN as a cross section. The first step, I want to determine what is the transverse loading in this section. So the quickest way to do this is we can use the shear, we can draw a shear diagram. So to draw the shear diagram, we can see like this. So this is X, and then we put into the few segment, this is V. And if you look at this one, the loading to this structure is symmetric. As long as this is symmetric, we can quickly determine the force here must be equal. Otherwise, we simply go to the static equilibrium to calculate the reactions. So once we have the reactions, then we can draw the shear. So the shear will be like this. Okay, so this is 1.5, and the value here is minus 1.5, and in kilonewton. Okay, so this is the distribution of the shearing stress, the shearing force, sorry. And again, this drawing is very quick, and I guess this one based upon our chapter 5. Okay, so if not familiar with this one, then try to go to exercise a little bit more. But anyhow, from here you can see in this segment, NN, it doesn't matter which exactly the location is, we know the value of V equal to 1.5. So for this case, the V equal to 1.5 kilonewtons. That section is here. So basically the section, for example, if we say expose the sections, the NN is here, and we know the magnitude of V equal to 1.5 upward or downward on this section, downward. Okay, so V equal to 1.5. So for example, if we would flip this section to here, okay, so that right now we look at is this viewpoint. So let me turn over to front of view. So that means here we have V equal to 1.5. On the other side, if we would pick the different viewpoint, say if I pick this free body diagram, so right now this section exposed is faced to left, so the V should be acting like this. Okay, so if we view from this viewpoint, the V will be upwarding. So let me put into kind of the comparison. So for that kind of the viewing, the V will be like this. Okay, we save it, and later I will make a note on this one. So how about this? We work on this one. So basically here, just show you, I want to tell you, either one you pick should be fine, as long as we pick the one, we keep everything consistent. So we use this one for our continued calculations. And now the Q. is we call the first moment of inertia. What is Q exactly? The Q, for example, say at the QAA. How about that? So here, let me redraw our section here. So AA is here. So Q represents what is Q? This is the slice we pick, right? And that is the cross sections. And that is a cross section we've been used in these formulations. And I want to try your memory. What is Q? Q is the Y bar times A. A is this area. Y bar is the position of this centroid of this area to the neutral axis of the entire cross section. Got it? So which means, let me call this is called the A bar, A star, and this is the centroid of the shaded area, and this is the neutral axis, and this is Y star. So that means Q will be equal to A star, Y star. Okay? Again, for this example, our beam is bending over like this. So neutral axis is horizontal one. When we've been bending over like this, that will induce transverse loading, that is vertical. Okay, that is vertical. So that means the quickest way to identify the orientation of the neutral axis is you simply determine the direction of the V, then the neutral axis should be perpendicular to V. Okay, so that is the quickest way. You don't have to think through from the very beginning of the derivation to now. You simply take this sum of rule, the rule of thumb or sum of rule for this one. And I is the moment of inertia of the entire cross section. So I is the moment of inertia of the entire cross section with respect to the neutral axis. Okay, not the shaded one, no. Okay. And T is the thickness. T is the thickness where is the thickness of AA. Okay, because the meaning is we're going to calculate the average stress over this area, and which is related to one dimension here, right? So that's the T. For this example is the AA distance. And so for this case, let me pick up the numbers here. To calculate the moment of inertia, and again, you have to follow up the chapter 4, and that really time consuming is you have to determine the centroid or the neutral axis. And let me skip the details. For example, here, let me directly give you, this is the neutral axis, and for that one, that is 68.3. Sorry, I forgot to give you the dimensions. So here is 60, and this dimensions here is 100 millimeter, and this one is 20, this one is 20, and then from here to here, that is 80. Okay, so based upon those dimensions, we'll be able to calculate the centroid. So the centroid of the entire section is there. That's the neutral axis. And I, based upon those informations, for this example, I is equal to 8.63 times 10 to the minus 6 meter to the fourth power. Again, to fix the two information will take time. Okay, it will take time, and be careful on this one. So now we can calculate. So therefore, at AA, the tau average along AA. That means we pick a level. AA is a little bit on the upper, so that means we calculate average actually is the shear stress along the level represented by AA. Okay? Okay, so that is the case. And to plug in here, V equal to 1.5, 1500 newtons. And Q, for this case, we need a little bit calculations. So A star is how much?